All right, so thank you guys. I guess in looking at the title for the second part of this talk and looking at the schedule, I was amused to see this is completely without coordination at all. That all of the words that are here in my title are almost identical to the words that were in Zhao Dongzhu's title, and in his words, it's. We see the same things. It's nice. It shows that it's reproducible. So I guess there are many similarities, and I'll talk to you a little bit about some of the cool things that we see and how they relate more broadly to the things that we heard earlier in the conference. And really, the goal here that I'd like you to take away from this talk is we're doing our best to figure out how you go from a picture like this, which is incredibly complicated, to some sort of understanding of what is really driving the microscopics of these systems. Why is it that you get certain phases in certain regimes, other phases in other limits as a function of various different experimental tuning parameters in the system? So the place that I'd like to start is very simple. Way back when, you learned about atomic orbitals, s orbitals, p orbitals, and in solid materials, of course, the atoms are arranged in particular crystalline lattices. And those crystalline lattices can be of different geometries. They can be made up of different atomic species, which of course have various different atomic orbitals that are occupied or unoccupied. And we learned early on in solid state physics about how you can take these orbitals, consider the hoppings between adjacent orbitals and atoms, and from that you can build up a band structure like this. And this already, if you just consider a single electron at a time, is enough to explain a tremendous amount of the physical properties of material systems as we know. That is, basically, as you do this calculation, you get a spaghetti diagram. We saw many of those earlier in the earlier talk this morning of different electronic bands. And all you really need to know is how many electrons do you have? You fill up these bands one by one until you run out of electrons in your system. And then where you end up dictates the property of the material. That is, at a single particle level, if you just park yourself in the middle of one of these bands, you expect to have metallic behavior, and the carriers are delocalized throughout the material. On the other hand, if it just so happens that you completely fill up one of these bands, and you have no more electrons left and your Fermi level sits in the middle of a band gap, then you have an insulator or a semiconductor. And so this is a picture of silicon here, obviously tremendously important technologically to our society, but it's really an example of a broader phenomenon that at the single particle level, at least, we understand and can predict very well when should you get a metal, when should you get an insulator. But of course, that's only half the story. In fact, the most interesting cases are where this naive understanding breaks down, and that often is associated with the role of interactions among electrons. And so one example, one celebrated example, is the Hubbard model, where you can think of simplest possible interacting system. You have a lattice of sites that the electrons can occupy, and there are two parameters that characterize this Hubbard model. One of them is the likelihood that an electron can hop from one site to an adjacent site. That's characterized by a parameter T. And the other parameter is that if two electrons try and sit at the same site, there's some Coulomb repulsion. There's some on-site local energy U that disfavors that sort of interaction. And so loosely speaking, you can think of the ratio of U to T as a really important tuning parameter within this model. That is, if you have some band, it has some density of states, and you park your Fermi level in the middle of that band, if you're in a limit where the interaction is small compared to the hopping can be related to the bandwidth of the system. So if you have a dispersive system and weak interactions, then you get metallic behavior, exactly as is predicted in the single particle limit. But on the other hand, if you have the opposite case, where your on-site interaction is very large compared to the hopping, such as might happen in a flat band system, then surprisingly you get an energy gap opening up as a result of this Coulomb interaction. Basically, you or this on-site interaction, basically it's disfavored to doubly occupy a site because it costs such a large energy penalty. And in that case, you get the band splitting into a lower Hubbard band and an upper Hubbard band, and you have charges basically pinned one charge per site. In this model, that's known as a Mott insulator. So this is the case for short-range interactions. You can also get similar transitions between itinerant behavior delocalized carriers and carriers which form some sort of electron-solid, periodic electron-solid from long-range interactions like Coulomb interactions that you have, for example, in two-dimensional systems where if the interaction is strong enough, you go from a case where you have a liquid electronic state where, again, the carriers are delocalized. There's no translational symmetry breaking. But as you crank up these interactions, as a result of long-range repulsion between the carriers, actually they arrange themselves into a solid known as a Wigner crystal that minimizes the mutual Coulomb repulsion between the carriers. And so it's this kind of idea of how interactions take you from itinerancy to from liquids to solids that I'd like to focus on in this talk. So again, the starting point is van der Waals materials, which, as I described yesterday, provide a really nice platform where you can tune a lot of the features. You can tune the Coulomb interaction I'll show you. You can tune the hopping, and you can really control things by controlling both the interlayer twist between different layers and also controlling external electromagnetic fields and so on and so forth. So yesterday I told you about twisted graphene systems. Today I'm going to focus on a different class of materials, transition metal dichalcogenides, that we heard a little bit about earlier in the conference, but I'll remind you of some of the key aspects of it. And again, so yesterday I talked about graphene systems, and I want to come back to this idea of different limiting cases. When you have a Moiré superlattice, you can have different regimes of that Moiré superlattice. And yesterday I talked about Hofstadter physics that comes about as an electron is moving through some periodically modulated electronic system in the presence of a relatively large magnetic field. You get a Hofstadter spectrum. It breaks up into particular subbands. And this limit you can think of as electrons moving in some weakly perturbing potential, a potential which isn't strong enough to localize them at a particular site, but nonetheless has important consequences. And oftentimes in graphene-based systems, this is the appropriate limit to consider. There's a second limit, which I didn't really talk about at all yesterday, which is the case where your Moiré potential is extremely strong, and it actually tends to localize your carriers at particular real space sites of the Moiré superlattice. And in general, this is the situation that is often realized in these transition metal dichalcogenide systems. So you can think of the picture kind of in the simplified cartoon where you have some Moiré potential. It may be very deep. It's deep enough such that carriers really like to sit at particular sites. You still have some probability of hopping between these sites. There's some on-site large Coulomb repulsion U, and of course these are still electrons that are making up the system, so you also have some extended long-range repulsion V that you get. And in this sort of scenario, just like I described in the introduction, you can get strong interactions where, for example, if you have one carrier per Moiré unit cell, then you have what is often termed a Mott insulator, where you have one carrier per site, and the hopping, the double occupancy, is basically forbidden by some large U. But because of this extended range interaction V, actually you can also get interesting phases at partial filling of one of these Moiré bands. For example, if you have one carrier out of, or one Moiré site out of every 3 occupied, then because of the long range repulsion, you also want to keep the carriers as far apart from one another as possible. And so you form what are known as generalized Wigner crystals. And that terminology comes from the fact that just like in a Wigner crystal, this electron solid is stabilized by the long-range Coulomb repulsion. But on the other hand, here you have a Moiré potential. And so that's pinning specifically where these electrons like to sit. And in fact, So there have been, many examples of these generalized Wigner crystals which have been observed, and in fact, even beautiful images that you can take using a scanning tunneling microscope, where you can set yourself exactly to these different filling factors, and you can see the triangular, the honeycomb lattice, and you can see how this pattern of real space charge changes as you add carriers to the system. All right, so that brings me to the outline of my talk. I'll tell you a little bit more about twisted transitional metal dichalcogenides. What's the starting material? You'll see that actually that has an important consequence in terms of the physics that comes out. I'll remind you again of the scanning single electron transistor technique that we use to study these systems. It's actually really, really helpful to have this sort of technique. I'll describe why for the transition metal dichalcogenide systems. And then I'll show you two examples of different combinations, different materials combinations that give rise, in both cases, to very interesting phase diagrams of states that have both charge order and also, so electron solids, and also delocalized topological fluids of various varieties that can be tuned by external parameters in the system. So in one case, we're in the Moiré atomic limit, and I'll describe what I mean by that, coming back to this idea of atomic orbitals and how they combine to form bands. And then I'll tell you about transition metal dichalcogenide homobilayer, so twisted tungsten diselenide, which is morally very, very similar to the twisted molybdenum ditelluride that you heard about before, and also exhibits some of these same topological features that we heard earlier in the conference. Okay, so transition metal dichalcogenides look like this. They consist of a metal atom, some transition metal, usually molybdenum or tungsten, and chalcogen atoms, that is sulfur, selenium, or tellurium. And they're arranged in this particular structure here that has the metal atoms sandwiched by chalcogen atoms above and below. And if you look at the top view image, actually they form a honeycomb lattice where the metal atoms sit on one sublattice of this honeycomb, and the chalcogen atoms sit on top of one another when looking vertically at the other sublattice. And what this does is it basically, there is some sublattice symmetry breaking, so you get a very large band gap between the conduction and valence bands. So these are semiconducting materials. Again, the low energy states, at least in the monolayer case, are sitting at the K and K prime points. I guess here K prime is called minus K. These are related by time reversal symmetry, but because many of these are very, very heavy elements, there is also strong spin orbit coupling in these systems. And so what you find is that even though you have both spin and valley degrees of freedom, there's some spin splitting that depends on which valley you sit in, that in one of the valleys you have carriers which are spin up. In the other valley, the low energy states have the opposite spin down. And so you have effectively one remaining degree of freedom, so there's a twofold degeneracy in this transition metal dichalcogenide system. So just like in graphene, as I described before, you twist two transition metal dichalcogenides together, and they form a Moiré superlattice. There are quite a bit of details that can go in, so it matters whether you have kind of AA stacking or AB stacking that is naturally occurring. These layers alternate, so you break inversion symmetry in the layers, and so it matters whether you twist and stack parallel or anti-parallel. I'll be talking about this AA stacking case throughout this talk, but just to point out that there can be differences there. These Moiré superlattices are not actually equivalent to one another. But again, when you have a Moiré superlattice, this is just an example band structure calculation for a twist angle of 2 degrees, you can get very, very flat electronic bands, just like in the magic angle graphene case. But in some sense, these transition metal dichalcogenide systems are actually much, much nicer than the graphene-based systems, because in the transition metal dichalcogenides, you don't have a specific single magic angle where the bands become flat. So actually, the bands are flat over quite a broad range of twist angles. We heard talks in molybdenum ditelluride up to 3 or 4 degrees, similarly for tungsten diselenide. But these bands remain flat, really over a range of angles. So when you make these experimental samples and they relax and you're upset, actually it's not so bad. You don't have to hit that 1.1 degree just right. But on the other hand, As you change the twist angle, you change the effective separation, the Moiré wavelength between these, you change the size of this Moiré Brillouin zone or Moiré, real space Moiré texture. And what that does is it modifies the effective on-site interaction U, effective hopping T. Both of these, as you make your Moiré wavelength larger and larger, actually both of them tend to go down. But the hopping goes down exponentially as you increase the Moiré wavelength, whereas the on-site interaction decreases more slowly. And so what that means is by tuning the twist angle and by tuning the Moiré wavelength, you can tune actually the ratio of the on-site repulsion to the hopping T over quite a large range. Shown here is nearly an order of magnitude. And so you can hope, at least by exploring different twist angles, to map out different regimes of this effective long-range hovered model that you have. And beyond that, as you change from material to material, as you change the composition, the starting point, the stacking, as I described, all of these things can have profound effects on the physics that comes out. And in many, many cases, as I'll show you, by applying electric fields or by applying magnetic fields and tuning carrier density, you can change the nature of the states that come out. So these are really a nice model system to explore. On the other hand, as is kind of common in Moiré systems, there are challenges. So one is common to all Moiré systems. You saw it in my talk yesterday that if I take a spatial cut across the sample in graphene, sometimes you get lucky and you have a super homogeneous sample over micron length scales, but usually you don't. Usually the variations are of order, say, a half a degree as you move a few microns from one spot in the sample to the other. And so this is just an image taken from STM. Not to pick on these guys, this happens to everyone, but you can see on a length scale, this is a 50 nanometer scale bar right here. Even on length scales of hundreds of nanometers, you can see a huge change in the Moiré wavelength, which has quite a strong effect on, at least locally, what the stacking configuration looks like. And so that makes global measurements, if you try and do transport measurements on these samples, it makes it really hard because now you're averaging over all of this length scale disorder that often comes out when you fabricate these samples. The other thing that really, really is hard about transition metal dipole cogenides is they're semiconductors. And you may remember if you try and make electrical contact to a semiconductor with a metal, you get a Schottky barrier. And so making these samples, getting good enough electrical contact so that you can actually measure transport properties is also extremely challenging for these semiconductor systems. We saw obviously earlier in the conference that it's possible, but it requires quite a bit of engineering and effort to work. And so it would be nice if we could find some sort of measurement technique which is less sensitive to the large resistance of the samples and can look locally so that you're only looking at a small uniform patch of this Moiré system rather than averaging over this entire field of view. So just to remind you, in case there are people who weren't at the talk yesterday or who don't remember, my group uses a particular approach using a single electron transistor as a scanning probe. Again, this is just a quantum dot or a metal island separated by source and drain electrodes. And this is a way to get Coulomb blockade physics where as you tune the electrostatic environment of the single electron transistor, you get a modulation in the current, which we can then use. We can measure that and extract out what is the nature of the local electrostatic environment. And we put this on the end of a tip. Our electrostatic environment is provided by the sample. We hook a lead up to it that fixes its electrochemical potential. And so as we tune the carrier density with a backgate, then that changes the chemical potential of the system, and there's a corresponding change in the electrostatic potential, which is what we sense with our material. And again, anytime you have a peak in the density of states, that means that the chemical potential doesn't change very rapidly. Anytime you have an energy gap or a low density of states, then you get a step in chemical potential or a peak in d mu dn, which is what we measure. So anytime you see a large signal in our measurements, that corresponds to a case where there's an energy gap in the system. All right, so the first sample that I like to tell you about is actually a heterobilayer twisted transition metal dichalcogenide. It's composed of molybdenum diselenide and tungsten diselenide layers. And in fact, if you go back to the theoretical literature, it was the very first twisted transition metal dichalcogenide system that was proposed as an interesting one to look at. It's interesting for a couple of reasons that I'd just like to highlight. So one of them is that in many of the previously studied samples, if you use different transition metal dichalcogenides, they may have different lattice constants. And so the Moiré wavelength depends on both the lattice mismatch and also the twist angle of any system. And when you have a heterobilayer, that means that as you decrease the twist angle, eventually this lattice mismatch term is what's dominating you, and it limits the Moiré wavelength that you can get, even if you go toward the zero twist limit. On the other hand, for lattice match compounds, so here this is an image I took from a review article from the Cornell group. They labeled it as homobilayers, which obviously will have the same lattice constant, but actually this molybdenum tungsten diselenide combination also has a very, very similar lattice constant. So it looks, as you decrease the twist angle, you can get to very long Moiré wavelengths. And in particular, I want to emphasize this low twist angle regime is the regime in which the ratio of the Coulomb interaction U compared to the hopping T is the largest. And so it going to lower and lower twist angles helps you get to this strongly or most strongly interacting limit. And it's interesting there. And one point I didn't make is the electrical contact gets harder and harder as you go to lower and lower density. So that, again, makes transport measurements significantly harder in this regime. And between that and the lattice reconstruction and local twist angle variations, then you really, really need a local probe to look at. So one nice thing is that you have lattice matching, so you can get to long Moiré wavelengths in the system. And the second unique property of this heterobilayer is that actually the Moiré potential is both very, very strong, of order 100 millivolts or so. That is, the potential wells themselves are quite deep. And also, it's almost perfectly triangular. So you can see that as you add charges one by one, they like to form very localized electronic wave functions at the preferred stacking real space stacking sites. And in fact, as you add more and more carriers per Moiré unit cell, actually multiple carriers like to sit in the same place because the Moiré potential is so deep. So this is a picture of our sample. Green and orange are the two transition metal dichalcogenide layers. Again, we can confirm that this is AA stacking. And I'll show you how we get this, but the twist angle of this particular sample is about 1.35 degrees or so, plus or minus 0.1 in different areas of the sample. So this is actually fairly homogeneous as a sample. But this twist angle is quite low, and it corresponds to a Moiré wavelength, which is actually quite long on the scale of transition metal dichalcogenide. So the rule of thumb that you should have in mind is the Moiré wavelength is about 19 nanometers divided by the twist angle. So the heterobilayers, the Moiré wavelength is usually 8 to well, 5, I don't know, I guess 5 to 10, depending on materials, nanometers from the lattice mismatch. And for these twisted molybdenum ditelluride samples that Xiaodong, for example, was talking about earlier, that corresponds to a Moiré wavelength at 3 degrees of, again, somewhere in the range of 5 to 10 nanometers. So on the scale, at least for transition metal dichalcogenides, this 15 nanometer wavelength is quite long. Again, we bring our tip close to this heterobilayer. You might ask the question, what electronic states are we actually looking at? Well, for kind of boring reasons, it's easier to dope holes into the system with our electrical contacts, and so that's what we'll be looking at. And because of the band misalignment between the tungsten diselenide and molybdenum diselenide, that means that all of the carriers go into the tungsten diselenide layer. So the molybdenum diselenide is useful for providing and producing a Moiré potential, but otherwise can basically be ignored for what I'll be showing you, and all the physics is happening in the tungsten diselenide layer. So before I show you data from our scanning single electron transistor measurements, let me compare a transport measurement on the same device between these two electrical contacts. You can see, okay, as I increase the backgate, or well, go to more and more negative backgate voltage to hole dope the system more and more and measure the resistance between through the sample, you can see, okay, there's some peaks that are occurring here. Maybe it has something to do with Moiré physics, maybe not. This is a 4K measurement just at zero field. But on the other hand, if we park our tip at this black dot here and measure locally what does the electronic compressibility look like, all of a sudden, you can see that there are very, very sharp peaks. More of them are resolvable. And the positions actually correspond. So there is some correspondence to the transport measurement, but we pre-screen these guys, and if there are peaks, we say, great, that looks promising, and we couldn't tell you anything about twist angle until we get these local measurements. You can see the dramatic improvement. It's like putting on glasses for those of you who are glass. Yeah. No, so okay, so this is done in a 4K dunker. That is, we dunk the whole sample in liquid helium. So I don't have data to show you at 1.6 Kelvin in transport, but actually what happens is because the electrical contact is challenging, actually the entire resistance goes up, and if anything, these peaks are often swallowed up by the insulating type behavior that you get from the semiconducting band gap as you approach the band edge. So actually it gets worse in transport. At low temperature, the charging becomes harder, and it's not that these peaks are appearing because of the low temperature, it's that these peaks are there because the technique is really a better way of looking at these samples. Okay, so what do we see when we look locally? So this is a measurement at a particular location in the sample. It has a twist angle of 1.33 degrees, which we can benchmark based on where we see different incompressible features that I'll tell you about. And what I'm plotting here is inverse compressibility. So on the scale, everything red here corresponds to an incompressible state. That means an energy gap in the system. Everything blue actually corresponds to negative compressibility. That comes about because there are very, very strong electronic interactions in these systems, and that gives an overall negative background just from exchange energy, which in these transition metal like chalcogenides is quite large. And I want you to focus first on this regime where we have relatively low magnetic field and relatively low doping, up to 2 holes per Moire unit cell here. This is 1 hole per Moire unit cell. And you can pick out, obviously, there are several vertical features which are appearing here. There's incompressible states, like a mod insulator, when you've filled this with 1 hole per Moire unit cell. There is a band gap also when you fill 2 holes per Moire unit cell. And you can see that there are other incompressible states at rational fractional fillings. These correspond to the generalized Wigner crystals that I was showing you before. So this is very similar to what had been seen previously in past measurements of transition metal dichalcogenides. But something interesting happens as you continue to tune the parameters. So as you increase the magnetic field further, what you find is that there is some abrupt transition that happens really over this entire range of filling where the generalized Wigner crystals weaken, and there's something diagonal which starts to appear past a magnetic field of about 6 Tesla or so. So there's some broad transition, and then as you go even further out, as you dope even more to higher filling of carriers per Moire unit cell, you can see that actually we're dominated now by these diagonal features. These are exactly the Hofstadter states that I described earlier. You can tell they have some non-zero Chern number because they're sloped, in contrast to the trivial states, which are the generalized Wigner crystals that I was talking about before. And then you have this funny region here that cuts through the Hofstadter states. And again, you have some vertical incompressible features. And if you look carefully, actually, you see that the fractional fillings at which they occur are exactly the same fractional fillings as we had before, but now modulo an extra integer filling. So you can break this up, and I haven't really motivated quite yet how I'm coloring this picture, but you can break this up into different regimes of different phenomenology, which are dominated by generalized Wigner crystals, by Hofstadter physics, or by something funky which cuts through them. So how should you think about this? Actually, I think the right way of looking at this is, remember we had very deep Moiré potential wells where the charges like to sit. This is a very large Moiré wavelength, And so you can kind of think of this system as consisting of many, many different potential wells, which are weakly talking to one another. And so you can think of individual electronic states within a potential well. The lowest energy eigenstates are sort of like s orbitals of atoms. Remember, these are twofold degenerate because you have this spin valley degree of freedom. And then after you've completely filled those s orbitals, there are also, because these are so deep, additional bound states that act as similar to p orbitals. And these p orbitals are more delocalized throughout space than the s orbitals. So if you think about what that means in terms of band structure in the system, because these s orbitals are so tightly localized, because the hopping effectively between these sites is so low, that leads to extremely flat electronic bands. Doping up to 1 hole per Moire unit cell, it's obvious you're going to fill one of these s orbitals. Then between 1 and 2, you have a choice now. There's some on-site repulsion that plays a role, and so there's some effective Hubbard U that opens up a band gap between this occupied s orbital and the next s orbital. Or, and remember this, at least in a magnetic field, will have, in general actually, must have opposite spin from the occupied band. And so that's one option, and we'll have opposite spin, say in a magnetic field, whereas you also have these more dispersive bands that come from the p orbitals. They're more dispersive because the p orbitals have a larger overlap. These p orbitals, of course, can have also many different spin or orbital contributions. And so the key takeaway is that as you ask the question, what states do you want to fill past 1 hole per Moire unit cell, you have 2 options. You can fill this upper Hubbard band, or you could fill this more dispersive band. The details of the splitting between these guys are based on the microscopics of the problem. But on the other hand, you can tune with a magnetic field just from a Zeeman type effect. These guys will have opposite spin. These guys can have the same spin. And so as you change the magnetic field, you can tune the relative separation and energies of these different bands. So we can cook up a simple model for the free energy of this sort of system. It takes into account some effective Zeeman energy splitting between the 2 different types of bands, the s orbitals and p orbitals. There's some density of states associated with the dispersive bands, and we put in some sort of Stoner type interaction between carriers in the flat and dispersive bands. And you can just ask a very simple question. For a given filling factor, if you try and minimize the simplified free energy model, what do you get out, theoretically? What do you expect? And so that's what's shown here in this schematic diagram. And already you can see that there's a good correspondence between the experimental data that we observe and this theoretically this theoretical prediction from this simple model. That is, in this region here where you have low magnetic field and low filling factor, you expect to occupy the second flat band, this other S-type orbital. Yeah, question? Okay, so that's a good question and possibly a charged question. So it depends on your definition of Mott insulator. So a lot of people in the field call these states Mott insulators. I think some people, including at my institution, will say a Mott insulator necessarily has to not have any symmetry breaking all the way down to the 0 temperature limit. And if you ascribe to that point of view, I don't think that it's quite fair to call this a Mott insulator. But so you would expect as a triangular lattice, you would expect eventually to get some antiferromagnetic ordering. So in that sense, it wouldn't be. But I'll point out that the energy scales are such that actually we are very much in a thermally disordered regime. So if you just think of the exchange T squared over U, T is of order, say, a millivolt or something like that. U is of order 100 millivolts. So the T squared over U is tiny compared to the temperature around 300 millikelvin that we're doing these experiments. So we're very much in the thermally disordered limit. Still, you have a huge band gap. So in that sense, the large interaction-driven gap still persists even though you don't have magnetic ordering. So whether you want to call that a Mott insulator or not is up to you. The physical situation is as described. Yeah. Okay, so in this regime, well, I should point here because this is a theoretical calculation. In this regime here, you expect to occupy the opposite spin S-type orbital. But at some point, the Zeeman energy overcomes this energy difference, and you prefer instead to occupy the more dispersive p-type orbitals. And it's exactly there, similarly in this regime, where you tend to see the Hofstadter physics dominating. So basically what we're seeing here is a difference in the ground state. You prefer electron solids when you're occupying these very, very flat electronic bands. The Coulomb repulsion is very strong and stabilizes those states. On the other hand, as you're occupying the more dispersive bands, you see Hofstadter states dominating. You have electron liquid situation. So these are realizing these two different limits all in the same sample, just tuned by changing the relative energies of different Moiré bands. And maybe the most interesting thing or most unique thing is this little purple strip here, where if you imagine sitting at 11 Tesla and increasing the number of holes in your system, well, in this purple strip, actually both bands, the flat and dispersive bands, are partially occupied. So as you're going up and up and up, you occupy first the dispersive bands. Then within the purple strip, actually, you start to empty the dispersive bands and occupy the flat bands. And this strip corresponds exactly to where we see these charge-ordered states. Interestingly, these are still vertical. So what that means is, and they occur at these rational fractions. So what that means is we have partially occupied flat bands, partially occupied dispersive bands, and both types of carriers collectively are somehow, I guess I should go to the next slide, sorry, are somehow cooperatively forming an electron solid, this sort of generalized Wigner crystal. And actually, we don't have a good microscopic picture for exactly where the charges like to sit, how this happens, but there is some combination of light and heavy carriers which together form a generalized Wigner crystal there. So this is kind of neat. I'll also point out that there's something that's kind of cool here. So as you go up in magnetic field in this lower region. So down here, you've doubly occupied the same orbital. So these form doubly occupied sites, doublons, which are singlets in this low magnetic field regime. But in the higher magnetic field regime, actually, they're triplets. That is, you have s orbitals and p orbitals of the same spin type, again, occupying the same site. We can extract out the energy gaps of across this transition of different generalized Wigner crystal states. And you can see there's a dramatic softening as you occupy the more dispersive bands and form this triplet state. But in some sense, this is similar to a singlet-triplet transition in a quantum dot system. And there's some funny gap dependence that we still don't understand why in the singlet regime there should be some increase in gap size as a function of magnetic field. But I think for the interest of time, I'll push that. Hold off on that discussion. So all of this is very robust. We can look in different parts of the sample in areas that have similar twist angles. We see almost identical phase diagrams. Actually, if we decrease the twist angle, that tends to flatten the bands, and this Hofstadter state disappears. There's an extra incompressible state that we see at nu equals 3. As we increase the twist angle, you get an extra Hofstadter state here, so basically, this is all consistent with our picture that when you have flatter bands, you tend to favor charge-ordered states, and when you have more dispersive bands, then you form this electron liquid and see Hofstadter physics emerging. All right, so to summarize, we've realized, I think, a kind of interesting limit in this very low twist angle regime with a long Moiré wavelength, where you can think of these Moiré sites in an effective atomic limit. And within a particular sample, you can actually tune between different physical regimes and realize interesting kinds of electron solids. So I want to put that aside and talk about one more example of an interesting physical system, which is a twisted homobilayer of tungsten diselenide. So in this twisted homobilayer system, the low energy effective Moiré sites form a honeycomb lattice of MX and MX sites. So in the zero displacement field limit, as we heard a couple of days ago, this forms a honeycomb lattice with a skyrmion layer pseudospin spin texture, and this endows the system with topological bands. So this was theoretically predicted by Alan McDonald's group first, and here I'm showing some follow-up calculations by Liang Fu and Trizep Devakul, showing that, in fact, as you tune the twist angle in this system, you can change what is the expectation for the Chern numbers of different bands, different Moiré bands for a given valley. So again, very similar to what we heard from Xiaodong Zhu's talk. So you can go through this, this topological phase transition. You can also tune it with an electric field, and so I'll come back to that later on in the talk. But this is a really interesting system to look at kind of different electronic states as a function of twist angle to see whether we observe this sort of topological bands and changes in topology. So here again is our sample. This one isn't quite as homogeneous. The twist angle varies between 1.1 and 1.6 degrees as we explore different parts of the sample. That translates to a Moiré wavelength of about 12 to 17 nanometers. So although the twist angle variation is relatively small, actually this is a factor of 1.5 in Moiré wavelength, so it has a pretty profound effect. And again, when we measure electronic compressibility at a particular spot, here I'm showing you data at 1.23 degrees, you can see as a function of hole filling factor, number of holes per Moire unit cell, there are peaks at integer fillings, 1, 2, 3, 4, and 6. These correspond to energy gaps that develop within the Moiré bands. You can see also the step-in chemical potential from integrating this. And so we'd like to know, are these trivial or are these topological? And the way to tell that is to apply a magnetic field and see how these states disperse. So from the strata formula, we know that if you have a state with a non-zero Chern number, then necessarily that will have a diagonal slope in a magnetic field. And indeed, if we look at the state at nu equals -1, there is an incompressible state which is sloped all the way down to zero magnetic field. So this is a quantum anomalous Hall state. We haven't done transport on the system, but at least strata should be believable. So you should trust that this is a quantum anomalous Hall state. At nu equals 2, we see different behavior. That is, something is vertical, so the total Chern number is 0. At nu equals 3 again, if you follow this thing down, you can see that there's a gap all the way sloped to zero magnetic field, so that also is a quantum anomalous Hall state. Now, in the second Moiré band, and at nu equals 4 again, you get something which is vertical, and so net Chern number of 0. So, so we have topological states at half filling. That is, we've presumably spin valley polarized the system as a result of interactions, and this gives rise to quantum anomalous Hall physics. The situation at these even fillings is a little bit unclear. It could be that this is a quantum spin Hall insulator. That is, you've occupied both of the Moiré bands, and one of them is Chern 1, one of them is Chern -1. That would give a net Chern number of 0, but there is a competing antiferromagnetic insulating state. So there are some transport reports that indicate probably this is a quantum spin Hall insulator, but we can't tell, we can't distinguish that from our measurements so far. If now I show you, so previously we were looking just at the kind of this low field region of the phase diagram. Again, as we increase the magnetic field further, you can see that in this high field limit, there are tons of Hofstadter states which are appearing. So this is really generic. If you're able to probe clean enough systems, these Hofstadter states, even in transition metal like chalcogenides, appear. And again, you can sort of pick out by eye, there is this transition between that separates distinct behaviors, that one behavior is favored at high field. This is presumably fully spin polarized, similar to the transition that I was showing you in the heterobilayer data, whereas down here we expect that we're partially spin polarized. That is, the first state occupies one of the spin valleys and gives quantum anomalous Hall physics. Presumably at nu equals -2, we have this scenario where you have both of the first Moiré bands occupied, but their topology cancels out. This transition here is the transition between partial spin polarization and occupying kind of just these two blue arrows alone. At nu equals 3, we have, again, this topological state with one of the spin valleys occupied. We think actually that we're in this scenario where both of these diagonal lines point off in the same direction. So we think we're in a limit where both of the Moiré bands for a particular valley have the same Chern number. So this is actually, you have to consider multiple bands, not just 2 bands. It's not just a Kane-Lee model, but actually you have to consider even more bands to get to a net Chern number of 0. And similarly, at 4, it's not shown here. We think we've occupied both pairs of Moiré bands, of the first 2 Moiré bands. Okay, So in the last 15 minutes or so of my talk, I want to talk now about how can we tune these states and how can we understand the physics that comes out in different regimes and these ground states. So this is, again, just to zoom in on what I've been showing you before at a twist angle of 1.23 degrees. But I told you that as we park our tip over different areas of the sample, we can now look at different twist angles. So actually, all this twist angle disorder is helpful for us. If you go to a lower set of twist angles down to 1.12 degrees, actually you see that instead of having a diagonal feature all the way down to zero magnetic field, actually the preferred state is just vertical at nu equals -1. So these now, in the low twist angle limit, are actually topologically trivial states, not quantum anomalous Hall insulators anymore. And similarly, as you go to higher twist angles, here I'm showing up to 1.5 degrees, if you look carefully at this nu equals -1 state, again, everything is completely vertical all the way down to zero magnetic field. And so actually, the topology, the quantum anomalous Hall physics that we observe is limited to a very, very narrow window right around 1.25 degrees or so. We can do a little bit better. We have additional data that I'm not showing you here, just not to overwhelm you in the slide, but we can quantitatively extract two things. One is the size of the energy gap at nu equals 1 at zero magnetic field as a function of twist angle or equivalently Moiré wavelength, and also the topology. So these red dots are the topological states. They exist in a very narrow window of about 1.2 to 1.25 degrees. To lower twist angle, to higher twist angle, the gaps become bigger actually, but are topologically trivial. And so we think there are actually two different topological transitions that are occurring here as a function of twist angle to possibly different trivial electronic states at nu equals 1. And similarly, you can do this, plot the same thing for the nu equals 3. In this same window of twist angles, you get topology of that state. And then at lower twist angles, you can see that it's, again, a trivial state. At higher twist angles, actually, we don't even see an incompressible state at nu equals 3. Presumably, the bandwidth is too large. Yeah.
1.5 degrees twisting on the yeah, there you seem to have like a feature that looks like a quantum anomalous Hall thing. It's not super prominent.
So you think this is something sloped? Is that right? You're picking that out by eye? Yeah. So actually, if you look closely, this color scale is probably not ideal for showing this. If you look closely, what you should believe actually is that up to about a half a Tesla, I think a few tenths of Tesla at least, it's actually vertical if you look carefully enough at low magnetic field. And then you get states which are coming out which look like they are sloped. A comment that I think is true and isn't really talked about a ton is, people talk about quote unquote Chern insulators at moderate or high magnetic fields, and in some cases relate them back to the topology of the bands at zero magnetic field. I think actually when you start to apply a magnetic field, it becomes very, very difficult to know, is the topology that you have coming from the underlying bands, or are you just seeing topology of the Hofstadter subbands that are there? So I'm taking the cautious approach, I guess I would say, of assuming that this may be Hofstadter physics rather than related to topology of the bands. But I don't have a good experimental way of distinguishing those two cases, or actually I'm not even sure they're even theoretically particularly distinct. Yeah, thanks. Okay, so the takeaway message is we can use twist angle here to change the apparent topology of the ground state of the system. You also heard earlier in the talk and earlier in the conference that displacement field is a tuning knob for the topology of the ground states that you get. So in the low displacement field limit, you expect the weight to be equally occupied on these two sublattices, which are partially polarized for a given site in different layers. But as you apply a displacement field, you favor all of the holes occupying just one of the layers. And so you form effectively a triangular lattice. This is a trivial insulating state. And so you expect the topological phase transition as a function of electric field as well. And indeed, we can use our tip to apply a local electric field to the sample, and just by changing basically the voltage difference between tip and sample. And so this is an example of an image of inverse compressibility as a function of effective displacement field now that we're tuning with our tip. and filling factor. And so you can see there's some incompressible state at nu equals 1. And as you increase the displacement field more and more, it starts to weaken initially. And then at the highest displacement fields, gets stronger again. So you might think maybe this is a sign of the theoretically predicted topological phase transition. We can explore that more. So in a magnetic field, a trivial state and a topological state will occur at different densities. So we can do the same sort of measurement now at 1.6 Tesla, where in this low displacement field limit, you can see the incompressible state is offset from nu equals 1. That's a sign that it's sloped in a magnetic field, that it's a quantum anomalous Hall state. Whereas in this high displacement field limit, you can see that the state is pegged right at nu equals 1. So again, at the same effective critical displacement field, you get a transition in where the incompressible behavior occurs. So this also is very suggestive. And finally, we can do one better. So we can look in the high displacement field limit and in the low displacement field limit as a function of magnetic field. And in the low displacement field case, you can see that this state is really sloped all the way down to zero magnetic field. So this is a quantum anomalous Hall insulator. In the high displacement field case, it's just vertical. Yeah, question?
So have you pushed up your displacement field enough such that it will disappear again, or are you worried about blowing up your device if you bring it?
Yeah, so this is a good question. So we are limited here. So the tip, we can induce, we can apply a potential difference between tip and sample, and this indeed gives us some tunability of the displacement field, but our tip is narrow. And so what that means is, you can sort of see it in this stylized image, what that means is the effective gating from the tip is different depending on where you are in the sample. Right under the tip, that's where your displacement field is strongest. As you move away, the effective displacement field gets weaker and weaker. You get less doping from the tip. And so actually, there's some inhomogeneity to the doping profile. That's why you see all these extra wiggles starting to appear as you go higher and higher in displacement field. And this is a capacitive sensor. So you're integrating with some aerial average signal from everywhere that's capacitively coupled with some appropriate weighting by 1/d. And eventually, if we go too far, then everything smears out so much that we have no hope of actually seeing it. So it's not a question of breakdown. It's a question of how homogeneously we can actually do this and get sensible data out. It's actually nice that there's a topological transition. Sloped versus not sloped is a really crisp distinction that makes it easier to tell what's going on. All right, good. So building up these same sorts of measurements taken now in different locations and taken at different displacement fields, we can build a full phase diagram of where do you get a trivial ground state and where do you get a topological ground state as a function of twist angle and displacement field. And so you can see there's this narrow dome of topology that occurs right around 1.2 to 1.5 degrees or so. We don't have a good answer as to what exactly the nature of these different trivial states are on either side of it, why the bands don't appear to be favoring a topological ground state. They're certainly predicted to be topological well past this twist angle, and that's something that we don't have a full understanding of yet. But actually, we heard today, so there's we heard earlier in this conference from Di Zhao that by considering piezoelectric effects, basically by considering shifts in plane and comparing effective ferroelectricity and piezoelectricity from polar effects that come from the local arrangements of the metal and chalcogen atoms, actually they have some calculations where in this regime where we see non-trivial topology, indeed they get the Chern number correct, and indeed the Chern number for the first two Moiré bands for a given value is the same. So this is consistent with what we observe. The topology, actually, they predict to go away at this intermediate angle that I was showing you. So maybe that's a reason we haven't looked yet at angles above at 1.7 and above to see whether there's actually a twist, a change in the Chern number to opposite Chern numbers for a given value at higher twist angles. But this may be at least an explanation for what's going on in our to turn the topology off on the high twist angle side. Okay, so I want to come back to this idea of the transition. So these very dark blue lines here correspond to changes in magnetization of the sample. And you can see they have a dramatic change in electronic behavior at filling 2 and around filling 3. So it's clear that changing Moiré bands, just like in the heterobilayer, changing which bands are occupied completely modifies the nature of the ground states that come out. At nu equals 3, in fact, this is a metal insulator transition, so we can look at nu equals -3 as a function of magnetic field, and there's some point at which it goes from metallic, basically, to quite insulating. Interestingly enough, actually, this is not just a magnetic transition. So it's tuned by magnetic field, but actually, if we change the effective displacement field for a given fixed magnetic field, you can also drive this metal insulator transition as a function of displacement field. So there's some difference in layer polarization at nu equals 3 or layer polarizability. And so we're still sorting out what possibly the ground state may be. But the takeaway is that actually both electric and magnetic fields can be used to tune many of these transitions that we observe. And the last thing that I'd like to say is that actually we can use Maxwell relations to go from our inverse compressibility data. This is a measurement at 1.45 degrees. If I go now to higher magnetic fields and higher filling factors, you can see that there's a series of these dark blue features that are cutting diagonally across. These negative compressibility features are signs of phase transition. So you saw that here, that there's a strong dark blue feature at these spin transitions. So the same is true for these transitions here. And in fact, from our compressibility data, we can integrate to get d mu dB, we take a cut vertically to get d mu dB, and Maxwell relations tells us that that's related to the change in Z magnetization with respect to carrier density in our sample. And so in this way, actually, we can figure out what is the change in magnetization throughout this phase diagram as well. And you can see that these diagonal features here correspond to magnetic transitions. And in fact, I think I won't spend the time to go through the details, but this corresponds to filling one Hofstadter subband at a time, basically flipping the spin polarization of subbands in this Hofstadter regime there. So the last point that I'd like to make is that if you look now at different angles, so if you measure at different local twist angles, in all cases you see these kind of series of dark blue features that correspond to the magnetic transitions that we were talking about before. But here they're plotted not as a function of filling factor, but as a function of overall carrier density. And interestingly enough, when plotted in this way, these magnetic transitions more or less all fall in the same window of carrier density and magnetic field space. So I've just plotted the first one for you here, color-coded by twist angle. You can see that they all sort of overlap. And interestingly enough, this dashed line is what you get for magnetic transitions just in monolayer tungsten diselenide. No moire, no second layer, nothing like that. Actually, if you have AB Bernal naturally occurring bilayer untwisted, it also is very similar to this transition. And I think the takeaway message is these are very, very close to where the magnetic transition occurs in monolayer tungsten diselenide. That means that although the magnetic transitions have a really dramatic impact on what sorts of ground states you realize in the Moiré system, on the other hand, where they occur seems to be primarily dictated by the underlying material. And so this is a hint, I think, that if you want to try and figure out where in different portions of phase space to look for different interesting states which may require magnetic polarization or may actually require not being polarized, then it may be helpful to look at the underlying material properties themselves to figure out what's the most promising place to look. So with that, I think I'm mostly done. So let me again acknowledge all the excellent graduate students who were involved in this work. So the heterobilayer data was taken by Jiachen Yu and Carlos Cometer. The twisted tungsten diselenide measurements that I told you about have been led by Ben Foudy with some support by Carlos Cometer as well. And we had some, again, very, very helpful theoretical discussions with Liang Fu and Tritep Devakul and others in Liang's group. And So let me just conclude. I guess what I've tried to tell you is that in these transition metal dichalcogenide systems, you realize something that is more like an effective Hubbard model than in the graphene systems. So you can look at this kind of very large twist angle limit where you have Moiré sites which are very far separated, and actually it's instructive to think about them as individual Moiré atoms. And by changing magnetic field, by changing carrier density, you can tune which of these different Moiré bands are occupied. And so you can induce magnetic transitions in that way. In other material systems like tungsten diselenide, you can tune not only the nature of which bands are occupied, but actually the topology of the underlying ground states. And I'm not sure how generic to make this. This is all in a relatively low twist angle limit, what I've shown you so far, but at least in the low twist angle limit, the tungsten diselenide material itself seems to be strongly enough interacting that is really dictating when you get different symmetry broken phases, at least as much as the Moiré physics is itself. So I think I'll end there, and I'd be happy to take any questions.
Yeah, in this twisted tungsten diselenide, there's a superconductivity observed.
Yeah, that's right. So, yeah, go ahead.
First of all, have you ever seen superconductivity, and also how you can tune it, and which you see that?
Good. Okay. So just for those who aren't aware, let me go to some backup slides. So this is two very recent archive preprints that show that in twisted tungsten diselenide, in a certain narrow window of phase space as a function of electric field and filling factor, actually in two very different regimes, by the way, there's been superconductivity which was observed. This is tremendously exciting. I think it puts twisted transition metal like chalcogenides on similar footing to graphene in both systems, both graphene-based systems and transition metal like chalcogenide systems. You can get fractional turn insulators, you can get superconductivity, and this is exciting for a whole host of reasons. Your actual question is, did we observe anything like this? So the answer is no, we have not, but the answer is complicated because using our measurement techniques, so the way you should think about the single electron transistor is you have some backgate underneath. You modulate the backgate with some gate voltage that induces an electric field to your sample. And if the sample is conducting, it screens the electric field, your tip is above it, it sees nothing. If the sample is insulating, charges can't come on because it's insulating, your electric field penetrates through and you have a large signal with your tip. Now this is great for thermodynamic gaps, but it's not good for spectroscopic gaps. So if you think about what happens in a superconductor, then charge can still move. It can still screen the electric field that you're applying with the backgate underneath. So basically, for us, it's very difficult to distinguish between a metal, which is screening, or a superconductor, which is screening. So it's not clear to me that we would see such signatures of superconductivity at all. These are at much higher twist angles than what we were looking at also. So it's a different regime of parameter space too, which may or may not play a role. We have been thinking about possible experimental signatures of superconductivity in compressibility measurements, and I think it's a really exciting direction to pursue, but I don't have anything experimental to say about it at this point.
So if there's no more questions, let's thank Professor Feldman again.